This is about similarity and slopes, and specifically how can we show that the slope of a line is consistent. We're going to use the concept of similar triangles and that of dilation to kind of explain how the rate of change, which is called slope, stays consistent or always is the same. Now, when we take a look at dilation and triangles, we can remember that when we took a triangle and we dilated, we would dilate from the origin. You could dilate from a point, but we're going to dilate from the origin to kind of help explain how this works. So we notice that one side measures 1 and the other side measures 2. If we were to change it by a scale factor of 2, in other words, I want to double the size of this triangle, I would put another triangle right there and show that 1 times 2 is 2 and 2 times 2 is 4. So that would get me my dilation. I can also dilate even larger, and here I have 1 times 3 is 3 and 2 times 3 is 6. So this one has a scale factor of 3. And we can use this idea of scale factor so that we can identify similar triangles or sides of triangles and the relationship with slope. And we must remember that slope is rise over run, therefore a fraction. And we can kind of tell the sides of triangles as far as rise and run. And the relationship, or the proportional relationship, or the fraction, that it would be similar. So for example, this side would measure 6 divided by 3, which is 2. Here, this would be 4 divided by 2, which is 2. And here we have 2 divided by 1, which is also 2. So we're going to use triangles to kind of help us show how the proportional relationship is shown on slope. Now, what we're going to do is take a look at it usually with rectangles, because this will explain it a little bit better. Here I have a rectangle that is 1 unit wide and 2 units high. What we're going to do is we're going to take a scale factor of 2, and we're going to multiply that even larger. And when we do that, that'll multiply this to give us 2, and on the top 4. We could do it again by a scale factor of 3, and again, based on the origin, we would draw a new rectangle out, and that rectangle would be 3 wide and 6 high. Let's do it one more time with a scale factor of 4. That would put us at 4 wide and 8 high. Now with these rectangles, let's draw a line through the upper corners of the rectangles and extend down through quadrant 3, so we can have a little discussion. Now when we cut rectangles right through the diagonal, we're going to create a bunch of triangles. Hopefully you can see them. We're going to analyze different triangles here. So we're going to start out here with triangle A. And triangle A will be this little one here. And we can see that this measures 1 across and 2 high. So if I was going to say the slope of the line using this triangle, or the change in the triangle, we're going to say it changes by 2 over 1, or that it rises 2 over 1. Let's continue and take a look at the next triangle, which we will call triangle B, a little bit larger here. And in triangle B, we're going to measure how wide this is here, and this is 2 wide and 4 high. Now being 2 wide and 4 high, we're going to say that this is 4 divided by 2. Again, rise over run, the change in y from this point to this point, the change in the y versus the change in the x. Let's do the same thing for triangle C. So we're going to go from this corner to this corner. So we're going to be 3 wide and 6 high. So that would give us 6 over 3. And we'll do it one more time with triangle D. And here again, we would measure 4 here and 8 high. So it would be a change of 8 divided by 4. Now let's take a look at these fractions individually. We know that 8 divided by 4 equals 2. We know that 6 divided by 3 also equals 2, as does 4 divided by 2, as does 2 divided by 1. So this constant number of 2 that keeps coming up over and over again for this particular line tells us that the slope remains constant no matter what points that I choose along this line. Now it was convenient to count when we're just talking triangles here, but we can get triangles pretty much from anywhere. So let's take a look at some other triangles here. Here I have triangle E, which is this one outlined right here, which this one here measures from this point to this point on the line. And sometimes we see that when we're talking about measuring slope. We'll pick 2 points on the line, not necessarily from the origin. And we can see that this is 3 wide and 1, 2, 3, 4, 5, 6 high. Again, triangle E would give us 6 divided by 3, which equals 2. We can take a look at triangle F, which is this little one here. We have it 1 wide and 2 high. And again, that would give us 2 divided by 1, which is also giving us a slope of 2. So we can see that through similar triangles, we can show that the slope remains consistent. It does not change, no matter what points we're choosing. Now let's take this a step further, and let's record some points for this line here. So I'm going to use the points 0, 1, 2, and 3 as our input, and we're going to come up with some output numbers. So obviously 0, 0, because that's where we are here. If I input 1, out will come 2. If I input 2, out comes 4. If I input 3, out would be 6. So when we're looking at this relationship, we want to know, is there a rule to establish that? And remember, when we talk about a rule, we're talking about an equation about the input and the output and its relationship. So we want to know, what is the relationship of the output to the input? Now we can tell by looking at the table of values that every time we put a value in for x, it doubles. 1 times 2, 2, 2 times 4, 2, 3 times 2, 6. So we're basically doubling whatever that input value is, we're going to double it. Now what's interesting to note is that this value here too is the slope. 2 over 1. We just were talking about that, right? That particular line had a slope of 2. This is the same line that we were talking about earlier. So this is showing a slope of 2. And isn't it interesting that the slope is next to the independent variable? We've talked about that before, how the slope is adjacent to the independent variable when we're talking about the dependent variable. Now let's take a look at another line right next to it here, and it's blue. And let's put in some points as well for this line. Let's put in 0, 1, 2, and 3. Now, some of the things that we might notice just by looking at it before we put in the table is that these lines are parallel. Well, when the lines are parallel, we know that they're never ever going to run into each other. Let's hold on to that thought and let's prove why that is. Let's get some points here first. So this would be 0, 2, and at 1, we're at 4. At 2, we're at 6, and at 3, we're going to be up at 8, I believe. Yes, at 8. Okay, so now let's take a look at the slope of this line. Let's compare points from here to here. We can see that this has a similar slope. It's going to be 2 over 1. So if we use that idea based on what we were just talking about, and we wanted to write a rule for this, we would start out with y equals 2x, because we know the slope is 2 over 1. Well, but the problem is, if I use this to explain this rule, if I put in 0, 2 times 0 is 0. It is not 2. If I put in 1, 2 times 1 is 2. It is not 4. So this isn't fully giving us the big picture. What's missing? Well, what's missing is that we need to add 2 more to make this rule or this equation work. So if I put a 1 in there, 2 times 1 is 2, plus 2 is 4. If I put a 2 in there, 2 times 2 is 4, plus 2 is 6. I put a 3 in there, 2 times 3 is 6, plus 2 is 8. So this new rule is helping us to establish this line and get those points. Now, let's take a closer look at this and see what's going on. If we look at this, we know that the slope is 2 because they both have the same angle, the same triangle through similar triangles. But what's different is this 2. Notice on the graph, this one has a difference of 2. It's coming right there in that spot. We see where it's starting at 2. Well, that means there's a connection here between what is going on, where those starting points are on the axis. So let's address that a little bit closer. When we look at this, we can look at these equations or rules, and we could say that, here we had plus 0, and we don't really need to show that. So that was why we were getting 2, just plain old 2x. Well, here we would add 2. Well, we notice that the number that it crosses on the y-axis affects the rule. it shifts it up and down. When we think about that, this has a special name. This is called the y-intercept, where the line crosses the y-axis. That tells us that's the y-intercept. So if we take that to be true, what we know, let's go to this point here, and let me go up 2 and over 1 and draw a new line in here. Let me fix it so that it's parallel, because right now it's not. Okay. And here now we have another parallel line. We can look at this line and we know right away what the equation this line is going to be. We know since it's parallel, we know the output is going to have the same effect on the independent variable. We are going to double it. But this time, instead of starting at +2, we're starting at -3. So we're going to take 3 away from what our original is. So this is how we can set up an equation just by looking at what's going on. So that should kind of give us an idea about similarity and slopes, and we'll talk some more about this y-intercept and slope and how it's all related in the next lecture.